My name is Carlo and I would like to present our work about our paper, where we concentrated ourselves on further developing the seated embodied locomotion travel method. First of all, why embodied locomotion, and here especially leaning? Well, leaning already has been proven to be a suitable alternative interface for traveling compared to the standard controller interfaces. There are already many implementations and interpretations of the interface. The basic idea that they all have in common is that virtual movement is influenced by an inclination of the user's body or parts of it. This includes speed and/or direction. Advantages of this method are, for example, a positive effect on self-motion, improvement on task performance compared to controller-based interfaces. It leaves users hands-free for other kinds of interactions, and the seated method comes with a higher cyber sickness mitigation. When using leaning, your upper body is basically representing a joystick which lets you steer through the virtual world. Unfortunately, seated leaning comes with disadvantages as well. A crucial one being is that leaning can trigger the locomotion interface unintentionally. Similar to how a controller makes use of a person's hands and prevents them from performing additional action, as that interface is already in use, embodied locomotion can result in the same issues with the user's body by binding it to acceleration and movement only. This makes it difficult to pick something up from the ground or look underneath a piece of furniture. In the case of joystick interfaces, this is not an issue because it can be released, and with leaning, this causes a problem due to the fact that we need to move and lean in order to perform other tasks in VR and can't release the joystick. You will unintentionally activate the leaning interface because as you will need to leave the dedicated null position. Our main goal was to create a solution to avoid these unintentional activations, to give users more control over their virtual and physical movements and avoid unintentional movements. We developed and tested different status control approaches that can switch on and off embodied locomotion interfaces. For this, we use well-established input modalities for VR interaction: physical buttons, voice, gestures, and a metaphor. The status control methods developed around these input modalities has led us developing the following 6 methods. First of all, we tried to use approaches to avoid any disruption of the embodied locomotion interface. 2 of our methods don't use a break. The first is our baseline method, where we implemented a classical physical-based collision avoidance system, which pauses the leaning locomotion interface when the user is about to steer into a physical object placed in the virtual environment. With this method, we try to explore whether it is possible to avoid the use of a passive or active braking mechanism by changing the classic behavior of the leaning interface. We try to apply a Gaussian function to the interface, so as you go further away from a certain point, your speed will start decreasing again. This way, it is possible to be at a zero speed when you are further away from the zero position. We came up with the standard controller button press and hold as one of the first methods to actively pause the interface. We used an easy-to-reach grip button for that. Our speech method allowing the user to pause the interface by voice input. In our implementation, we selected the word pause to pause the interface and start to resume it. The back escape method uses a user's physical movement as a trigger to deactivate and reactivate the embodied locomotion interface. Leaning back into the pause zone deactivates the interface, allowing the user to move freely without unintentional activation. The user must lean forward into the intersect dummy object, in this case the sphere, to reactivate the interface. Our dual-state method is a hoverboard, which also requires the use of a controller, but also offers visual and sound feedback to the user. The board is purely virtual and doesn't need any additional devices. It can be activated by putting it in front of your body and deactivated by returning it to your back. We created a simple task-oriented virtual environment, evaluated each method using a within-subjects design with a total number of 18 participants, of which we have 14 males and 4 females, with a median age of 31.5 years. Each participant had 15 tasks to complete for each status control method. First, they had to move between 5 cubes at different heights and look underneath them to complete each task. Following that, they collected an object and moved between another 5 cubes and looked underneath them to complete the next 5 tasks. Finally, they collected a second sphere in their other hand and moved between the last 5 cubes and looked beneath them to complete the final 5 tasks and therefore the overall objective. Looking at the results here, the SAS scores of the methods rated by each participant to the right. On the left, the completion times of all participants, also for every method. The main findings were Gauss, which seemed to require a steeper learning curve than the other methods. When only one hand or neither were being used to hold a sphere, the hoverboard and button performed best. Unsurprisingly, the opposite became true when the second interaction task blocked the controllers completely. What was really unexpected was that despite the time to complete the movement to deactivate the hoverboard, the overall completion time using this method did not vary too much from button. The SAS scores on the feedback received afterwards from participants showed in favor of the hoverboard method. Overall, we can say the best choice for a status control method for seated leaning-based locomotion interfaces always depends on your application. In our work, we were able to show that status control methods should be used together with embodied locomotion interfaces when the application focus is not purely traveling. Controller-based methods perform best overall, with the pure virtual hoverboard method being the one that stands out. This method did not only seamlessly integrate status control in an immersive manner, but also potentially complete the leaning metaphor. Further recommendations strongly depend on the amount of times your application needs to use brakes, needs to travel backward, or has colliders. We can only recommend not to use Gauss.